Hey all, this is Mr. Yeager. One last video kind of summing up graphs, kind of just putting everything together one last time and then doing a quick practice problem with it so we kind of get the idea of how to interpret some. This is a good kind of comparison chart. Again, you can find it on It's Learning. So if we go through it real quick, let's kind of go through what everything essentially means. So for displacement time graph, the y-intercept. The y-intercept would basically be the initial displacement. Okay, I'm just going to go down this whole list first. It would be the initial displacement, okay, where you start. Actually, we'll go across. What is the y-intercept on velocity time graph? And once again, it's the initial this time velocity. On acceleration time graph, it would be the initial acceleration. Okay? So if you do have a y-intercept, it's just saying that you're not starting at 0. Okay? It could be 0. The y-intercept could equal 0. All right, the slope of the tangent line. In other words, what is the slope? The slope on a displacement time graph is velocity. All right, let's go and finish this section. A positive slope would mean a positive velocity. A negative slope would mean a negative velocity. And a zero slope would mean velocity equals 0. Okay? That it's not moving. You're at rest. I mean, you can fill that out. Okay? I'll put that with that one. It's at rest. I don't want to write it with these two, though, because we don't know whether it's accelerating or not. On a velocity time graph, the slope is acceleration. I'm going to abbreviate there. Acceleration. Positive slope means positive acceleration. Negative slope, negative acceleration. Again, it doesn't matter which side of the axis it's on. Okay? And a zero slope would be zero acceleration. All right? On an acceleration time graph, slope of tangent line, all this stuff means nothing. Okay? There is nothing to deal with the slope with it. Okay? Again, I guess the only thing you could technically say is that the positive slope would mean the acceleration is increasing, negative slope, the acceleration is decreasing, zero slope, constant acceleration. But again, that's hopefully kind of understood. All right, displacement time graph. You're going to see acceleration time is going to be a bunch of x's. Displacement time, what would a straight line represent? I'm thinking a straight sloped line. That would mean that you're going a constant velocity. Constant velocity. That's what that would mean. A curved line, I'm just going to write down, it only means that you're accelerating. Obviously, we might have to be a little bit more, you're going to have to be more specific when, obviously, is it speeding up or slowing down. But a curved line definitely means you have an acceleration involved. What does a straight slope line on a velocity time graph mean? It means you have a constant acceleration. I'll go and fill this one out. Even though this one's not going to really be used, a curved line would mean that you have a changing acceleration, but that's not going to happen very often. What would be a straight slope line on acceleration time? I guess we'll do that, is that you have a changing acceleration, and I'm not even going to list anything for a curved line. That's not going to happen. The area under a curve on a displacement time graph means nothing. Means nothing. The area under a curve on a velocity time graph is the change in displacement. The area under a curve on acceleration time graph is the change in velocity. Okay, that's correct. All right. I didn't say that back on that video with acceleration time. Again, acceleration time graph doesn't tell you what the velocity is. It's telling you how the velocity is changing. Curves coincide. That just means you have at the same displacement. Objects are at the same displacement. If they coincide on a velocity time graph, they're at the same velocity. And on an acceleration time graph, you have the same acceleration. Again, curves coincide, meaning that you have two curves coinciding. When is the object stopped? It is stopped on displacement time graph whenever you have a flat line. Okay, I'll write underneath here, zero slope. When are you stopped on a velocity time graph? When on x-axis. Okay, when v equals 0. When are you stopped on acceleration time graph? You don't know. It doesn't give you that information. Again, acceleration time graph doesn't tell you how the object is moving. Okay? When do you have uniform acceleration? In other words, a constant acceleration. What would you see? Okay? On a displacement time graph, you'd have a curve. On a velocity time graph, you'd have a straight slope. On this acceleration time graph, uniform, you'd have a flat line. Flat line, not at zero. Okay, you're above or below the x-axis. All right. I want to add one more thing on here, especially since, again, unfortunately, I forgot to do it on the velocity time video. Let's add one more category. When do you turn? When do you know you turn? On a displacement time graph, on a velocity time graph, and on an acceleration time graph. Okay? On a displacement time graph, you turn when the slope changes directions. Okay? When you go from up to down or down to up. Okay? You have to have the slope go, like, I'll just draw it. It has to go up to down. Okay? Right here is the turn. On a velocity time graph, we never talked about it. On a velocity time graph, when would I turn? Again, I turn when the velocity goes from positive to negative or vice versa. Well, how do I change velocity then? Well, where am I positive velocity? Positive velocity is above, negative velocity is below the x-axis, below the zero line. So on a velocity time graph, you turn when you cross the x-axis. When you cross the x-axis. All right, that is where you turn. The idea is the object is slowing down, slowing down, slowing down to zero in the positive direction, this whole time going positively. All right, at this point, he stops, turns, and is now headed in the negative direction and speeding up. Okay, on the acceleration time graph, guess what? We have no idea. Okay, again, because that's not telling us how it's moving. Acceleration does not tell us that it's even moving. What is its velocity? We don't know. We can again figure out the change in velocity, but it won't tell us about the turning for it. Okay? So that is one piece. The second thing I want to again go over is that the displacement time graph, the velocity time graph, and the acceleration time graph, when we're trying to figure out how one compares to the other, remember, I take this as when you want to go down this chart, when you want to figure out the velocity time graph from the displacement time graph, you look at the slopes. Because again, the slope of a displacement time graph is the velocity. And again, the time all stays the same. So if you find the slope for the first 5 seconds, now you know the velocity for the first 5 seconds. Okay? Same thing going from velocity down to acceleration. You look at the slope. But at the same time, what if it wants you to try to figure it out, you know, from the bottom up? Well, going up, its area means the above graph. If I find the area of the acceleration time graph, I know what the velocity, how much the velocity has changed. Now, I will tell you, when you go up, there could be multiple answers. There's multiple ways that we could see a velocity time graph based on an acceleration time graph. All right? And I'll show that really quickly. Same thing for velocity to displacement time. But slope takes us down, area takes us up. It also shows you why there is no slope after the acceleration time graph, and there is no area above the displacement time graph. There is nothing to take the area on. So let me just quickly show you this, what I mean. Let's say, for example, I have an acceleration time graph. I'm going to keep this simple, where this is 2 for 5 seconds. Okay? And I say, I want you to create the velocity time graph that would match with this. All right? There's actually multiple answers. All right? This is saying that the acceleration is 2 meters per second for 5 seconds. So let's figure out the area. Well, that would just be 2 times 5. It's a rectangle. So the velocity has changed 10 meters per second. Positive 10 meters per second. All right? That could mean, on a velocity time graph, one of 2 things. Again, you don't know what the initial velocity is, so let's just say you start at 0. All right? Well, if it's changed 10 meters per second in 5 seconds, that means I started at 0, I got to 10 in 5 seconds. Guess what? What would the slope of this line be? It would be 10 divided by 5. This is equal to acceleration. It's 2. How about that? The thing is, it could also technically be this graph. You could be at negative 10 back up to 0. You could be below. So the thing is, this is actually telling you 2 different types of motions. The first one up top is telling me that I have a positive v and a positive a, and I'm actually speeding up. This second one is telling me that I have a negative velocity and a positive acceleration. It has to be positive. My line is positive too. But this is what I'm saying. Acceleration does not specifically tell you exactly what's happening. It's telling you how something's changing, but it doesn't tell you exactly how it's working. And so you can see both of these graphs are possible interpretations of actually that very simple line up top. Okay? We will never have to go from this up to a curve. We might have to try to go, what would the curve look like? Okay? What would the curve look like? So actually, let me take a step back here. All right? What would the curve look like for this graph? I'll go to the next page. Go to the next page. All right? For velocity time graph. This one, you're not going to have to be exact. You'll just say, what would the displacement time graph look like? Well, you have to think about it. This is a positive v and a positive a. So what does that mean? It means that it must be sloping up on a displacement time graph, and it must be getting steeper. It must be curving. So this would be a correct interpretation. All right? If you match the top graph with this graph, you're correct. All right? What about the second one that I had? All right? This was velocity time. This was negative v, positive a. How would I look at that? Negative v. On a displacement time graph, that means I'm sloping down, but at the positive a, that means I'm slowing down. So it would be something like this. All right, that would be the interpretation for the other graph. All right, because again, this right here, the one on the right, this is telling me negative v, negative slope, but it's getting slower. So positive a, they have to be opposite signs to be slowing down. All right, so one last thing we're going to do together with this is let's look at a couple quick problems. I'm going to go probably pretty quickly through these. Woo, that's a lot of stuff. All right, let's interpret this particular line. All right. I'm not going to answer the questions. I'll basically answer it while we go through it. Okay? So, I want you to interpret the motion the entire time. So basically each letter represents a different section of motion going on. Okay? Alright, this is a position clock that's time. Position time graph. Okay? So let's figure out what's going on. This is position time graph. How do I interpret this? Slope is velocity. Slope equals velocity. So I can do it. Let's do all the velocities first. A, it's a flat line, so velocity equals 0 here. B to C, the line's going up, so that's a positive velocity. C to D, line's going up, positive velocity. D to E, line's still going up, so that's a positive velocity. E to F, negative velocity, line's going down. E to F to G, line's going down, negative V. Okay? So there you go. You've taken care of all the velocities. And I know you're probably going, I know what certain areas are. I know what certain areas are. Let's go through it step by step. Okay? Let's do all the areas that aren't curves. If there's no curve, acceleration is equal to 0. All right? And now you can probably interpret those areas. So right here, A to B, you're at rest. V equals 0, A equals 0. We already knew that because V was equal to 0. C to D, you're at a constant V. Constant velocity. F to G, constant velocity. Okay? Now what we have left are these curves. All right. At B, it's getting steeper. What does that mean? That means the slope is increasing. I'm speeding up. In order to speed up, I must have acceleration and velocity at the same sign. This must be a positive A. D to E, slope is getting smaller. I'm getting slower. I'm slowing down. The line's going flat. When the line's flat, technically I'm resting for a moment. This has to be negative A. Over on this side, the line is getting steeper. The slope's getting steeper. That means I'm speeding up again. That's a negative A. If I ask where do I turn, that would be at E. E is where I turn. I turn for a moment. Okay? And start heading back in the opposite direction. All right? One last problem. Let's look at a velocity time graph. You can see no curves because curves are too difficult to do on this. So this is a velocity time graph. We're going to do the same thing. Okay? All right, let's start with velocity. Well, velocity time graph. Okay? All I care about is it above or below 0. Okay? So this one right here is positive V. This right here is positive V. I have a lot of people mess that up. Negative V, negative V, negative V. I'm on 0. This is B equals 0. Okay? The slope is the acceleration. So if I have no slope, I have no acceleration. So A equals 0. A equals 0, A equals 0. Let's go ahead and interpret those. This is moving at a constant speed. This is moving at a constant speed in just the opposite direction. Constant speed, constant velocity, same thing. And this is at rest. All right, what about the rest of them? The slope is acceleration. The slope is going down. This is a negative acceleration. This is a negative acceleration, even though it's below the line, still going down. Over here we have a positive acceleration. From here I can now go, oh, opposite signs, this area is slowing down. That makes sense too because I approached 0. Down here I'm speeding up. I'm just going to write speed. Over here I'm slowing down. I'm approaching 0 again. Where do I turn? I turn at 3. Okay? I do come back to the x-axis at 7, but I don't specifically turn. Basically, I head out a particular direction, and I stop, and I just rest the rest of the time. Okay? So turning is when you cross the x-axis. Obviously, the last thing I could technically do is I could figure out the areas and go, how far did I actually travel? Okay, we could figure that all out. All right? So again, that's how we're going to attack these graphs throughout this year and in this unit. All right, thank you.